Hi, this is Mr. Pinter. Welcome back for Chapter 1, Part 3 on harmonics, impulses, and step functions. Let's start by talking about the harmonics of a continuous time complex exponential signal. So recall from our last lecture that if we have a signal x of t that is shown here mathematically as a complex exponential function, e to the j omega t, remember that omega here represents the fundamental frequency of this signal. We can use Euler's formula, for example, to express this complex exponential as a cosine and a sine term, which oscillate with the frequency, the radian frequency of omega. So what are harmonic frequencies? Well, harmonic frequencies are simply multiples of the fundamental frequency. So 2 omega, 3 omega, 4 omega, and so on and so forth are the various harmonic frequencies of this signal here. So that's all that really means, is a multiple of the fundamental frequency. The kth harmonic of this signal could be represented as k times omega. So the idea here is that the harmonics, we could write them out as x of k of t is equal e to the jk omega t. So notice now the frequency here is not just omega, it's k times omega, where k is a integer. One of the key things here is that for continuous time signals, there are an infinite number of harmonics for any fundamental frequency omega, because k can take on any value all the way up to plus or minus infinity. We're not going to do too much with this concept here in Chapter 1 or 2, but in Chapter 3, this will be a key idea when we talk about Fourier series. Now, what about for discrete time? Well, discrete time complex exponential sequences also have harmonics. And so likewise, we can define these harmonic frequencies as if omega is our fundamental frequency, as shown here, then our harmonics are 2 omega, 3 omega, 4 omega, and so on and so forth. However, there's one major difference here with discrete time sequences. Once we go high enough here, we'll actually return back to our first harmonic. And this will be, I'll show this a little more clearly on the next slide. And I'm not going to go through all the gory details here to prove this, but it turns out that there are only n distinct discrete time harmonics, where, remember, n is the period or fundamental period of the sequence. So in other words, if our sequence repeats itself every 8 values, every 8 ticks of n, then our period n, big N that is 8. Now what that means is there will only be 8 harmonic frequencies. So why is this? Well, one way to show this why is, remember that for discrete time sequences, omega, what we call the discrete time frequency, is really an angle. It has it carries the units of radians, or more technically radians per sample. But remember, the thing about radians is when you go around a circle, you can only get as much as 2 pi radians and you're back to where you started from. So what happens here with these discrete time sequences, let's say this is omega represented right here. This would be 2 omega, 3 omega, and so on and so forth. But once we get all the way to n times omega, where n is the period of this sequence, then we're back to where we started from and we just start repeating ourselves. So in other words, the n plus 1th harmonic is the same as the first harmonic, omega. Okay, let's change gears now and look at a couple of important functions that we're going to be using over and over in this course. The first one is the discrete time unit sample, and also we're going to look at the discrete time step function. So the discrete time unit sample is also called the unit impulse, or mathematicians like to call it the Kronecker delta function, with this is the delta symbol right here. So this unit sample function, or delta function, is usually designated as delta of n. And remember, again, those little square brackets remind us that this is a sequence in discrete time. This is not a continuous time function. So this is, perhaps the simplest sequence we can think of. Notice it just has a single value of 1 right here when n is 0. And the rest of the values of this sequence are all 0. So this is our unit impulse or unit sample or delta function in discrete time. Likewise, the discrete time unit step function is literally, it's very descriptive, it's a step. We go from 0 up to 1, and this just keeps going and going. And notice the step is at 0. All right, so let's do a couple activities, a good warm-up here for our lecture. Go ahead and sketch the following sequence. X of n is equal to delta of n minus 2 plus 2 times delta of n plus 3. So that's your first task. Now remember, these are of course delta functions, and you already know how to handle these shifts here. We did these in one of the previous parts of this chapter's lectures. The second activity is to evaluate the sum from n equal negative infinity to positive infinity of the delta function. And here's a hint here. The answer is a number, not a sequence. And then also, our last activity, evaluate the sum over all n of the delta, this is the shifted delta function, delta of n minus 1. So go ahead and pause the video here and see if you can figure out these answers to these activities. Okay, so for the first activity, we were asked to sketch the sequence x of n, which is equal to delta of n minus 2 plus 2 times delta of n plus 3. So this first term here, this is a delta function, and notice it's delayed by 2 that's because of the n minus 2. So the delta function, instead of being at 0 here, we shift it over 2 to right here, and so there's our first term. Now the second term here is 2 times a delta function that has been advanced by 3, n plus 3. So we have to start here at 0 and move to the left 3. And notice the height of this delta function is now 2 because of this coefficient out in front. So here's the sequence x of n as described by this equation here. The next one was to evaluate the sum over all n of the delta function. Well, we can just look at this, and it's pretty easy to tell that all you're going to be doing is adding a bunch of zeros, and then there's a 1 here, so the sum is 1. And likewise, if we shift the delta function over by 1, or any number for that matter, notice if we sum up all these values, we're still going to get the same value of 1. Here's a few more activity examples for you to try. So suppose you're given the following sequence. X of n is equal to 1/2 to the nth power. So given that, you're asked to sketch the following sequences. Part A, y of n is equal to x of n times u of n. Now remember, what is u of n? U of n is the step function. Part B, y of n is equal to x of n times delta of n. So this is the unit sample or delta function. And then the last one, part C, y of n is equal to x of n times delta of n plus 2. So in order to do these types of problems, plot x of n, which is right here, and for example in this one, plot u of n separately. Maybe overlay them, one above the other on your paper, and then just move across the sketch for each value of n, just multiply their individual values to get your answer here. So again, go ahead and pause the video and see if you can figure out and make a quick sketch of what these sequences would look like. So here are the solutions to our activities. So we were starting with this sequence x of n equals 1/2 to the n. So I went ahead and sketched that here, at least a few of the values of it centered around 0. So I went from -2 to +2 just to get an idea of what those values are. Now in order to figure out what y of n here is, we need to multiply this function here by a step function. But the key thing about a step function is it's 0 everywhere to the left of 0. So that means all these values here over to the left of 0 are going to end up being zeroed out because they're multiplied by 0. So all we really have to do is consider this function here, x of n, starting at 0 and going to the right. So we end up with 1, 1/2, 1/4, 1/8, and so on and so forth. For the next one, we're multiplying x of n, which is shown here again, by the delta function. All right, now the delta function, remember, has a value of 1 right at 0. So we're going to multiply that times this, and we have 1 here, and of course 1 here. That gives us a 1, and all the other values of this sequence are going to be 0, because the delta function, remember, is 0 everywhere except when n is equal to 0. So this is our sequence for y of n right here. The last one was, let's see, y of n is equal to x of n times delta of n plus 2. Now notice delta of n plus 2 is 0 everywhere except when n is equal to -2. So this delta function here forces n to be -2, and that's the only really value of n we care about. So when n is -2, notice our sequence here, x of n, has a value of 4. And so all that's going to come back then is the value of x of n at -2, which is a 4, and all the other values of the sequence are going to be 0. So make sure you understand how to do these basic manipulations with the step function and the delta function before you go on, because these are key fundamental ideas for this chapter. One other thing we can do with the delta function is something called sampling or sifting. And we're going to deal with this a little bit more actually in chapter 2, but this is a good time to introduce some of the basic concepts right now in chapter 1. So let's imagine we have some sequence x of n, which is shown here. And let's say we want to multiply this sequence by a delta function, delta of n, which is shown right here. So this is, almost exactly like one of the activities you just did on the last slide. So what happens here is all these zeros here basically kill all the values of x of n, and all the zeros over here likewise kill all these guys over here. The only one that survives, of course, is the one where the delta function is, right here at n equals 0, because when we multiply the 1, it just basically returns the value of x of n at 0. So the result, when we multiply this sequence times this sequence, is we get a single value that basically is a sample of x of n at n equals 0. One way to kind of look at this mathematically is we have x of n times delta of n, and delta of n, this delta function, forces n to be equal to 0 in x of 0, and x of 0 is just a number. All right, so imagine we want to add up all of the products. So this is the sum of the products of x of n and delta of n. Well, using this idea here, we have x of n can be changed to x of 0, because that's where it is getting sampled here. And x of 0 is a number, not a sequence. So we can pull it out of this sigma symbol, out of this summation, and bring it out in front. But look what's left. Inside the green box here is the sum of the delta function over all n, and we already did this in an activity a couple slides back. That, of course, is just equal to 1. If we add up all these zeros and the 1 and all these zeros, we just get a 1. So this sigma, or summation here basically goes away, and we're left just with the number x of 0. And we can sort of generalize this idea by using a shifted delta function. So in this case, we're going to take x of n again, and this time we're going to multiply it by delta n minus k, where k is the shift in the delta function. So we've shifted it over some k value of n. And when we multiply this together, now of course the delta function, which is sitting over here at n equal k, is going to sample the kth value of x of n, which is x of k. So the result here, and here's when we multiply in all of this times all of this, we get just this. We get the kth sample of x of k. So, doing the summation again, if we have the summation over all n of x of n times delta n minus k, well, this delta function here forces n to be equal to k, which is right here. And thus we can switch this x of n to x of k, and since x of k is a number and not a sequence, we can bring it outside of the summation, and we're left with the sum of the delta function, which has been shifted, but that's still equal to 1. In other words, when we add up all these zeros, there's the 1, and all these zeros here, we still get the same 1. So all this stuff in the green box here goes away. It's a 1. So what we're left with is a number, the kth value of the sequence x of n. What we just described on the last page was basically a derivation of the so-called discrete time sampling property. It says that the kth value of a sequence, that is x of k, is equal to the sum of the product of the x of n, the whole sequence, multiplied by a shifted delta function, shifted over where n is equal to k. So again, one way to think of this is that the sequence x of n, right here, is sampled at n equal k. So here's our original sequence x of n. The kth value of that is shown right here. That's x of k, and that's given by this summation here. So here's a couple, or an example activity for you to do. Here's we're given this same sequence again. X of n is equal to 1/2 to the nth power. Go ahead and evaluate the sum of x of n multiplied by delta of n minus 2. If you don't recall what we just did, go ahead and look back on the last slide, but you're basically going to use the sampling property here. So go ahead and pause the video here and see if you can figure this one out on your own. Okay, so the solution to this is we want to evaluate the sum of x of n times delta of n minus 2. Well, delta of n minus 2 selects or forces n to be equal to 2. So we can replace x of n here with x of 2, and x of 2 is just a number. So we're going to bring that outside of the summation, and we can evaluate it. What is x of 2? Well, when we plug in a 2 here, we get 1/2 squared, which is 1/4. And then what's left is the sum of a shifted delta function, and of course that's just equal to 1, as always. So our final answer is 1/4. Let's now move on to the continuous time version of these same functions that we just looked at, the unit impulse or delta function, and also the step function. So let's start with the continuous time unit impulse function or delta function. Also, it's called mathematically sometimes the Dirac delta function. So this one is a little bit different and not quite as simple as a discrete time case. One way to express it mathematically is that the delta function, delta of t, is the limit as delta, this is a uppercase delta, goes to 0. For when t is not equal to 0, the delta function has a value of 0. And when t is equal to 0, the delta function has a limit of 1 over delta. So you can kind of think of this thing as it's 0 everywhere, except when t is equal to 0, it actually has an infinite value. So how do we describe or deal with something like this? Well, you can think of the delta function, delta of t, as a brief, strong pulse of duration delta and height 1 over delta. So let's take a look and see how we could plot this. So the delta function here, remember it has a height of 1 over delta, shown right here, and its width is delta in time. All right. Now notice if we were to figure out the area of this impulse here, all right, by integrating it or just figuring out the area of the shaded area, we have height times width. We have 1 over delta times delta is just 1. So this is one of the key features of a delta function. It has an integrated area of 1. So now let's take the limit as our delta here gets smaller and smaller and approaches 0. So the width is getting smaller and smaller, and the height, 1 over delta, is therefore going to get larger and larger, but of course the area remains at 1. So what happens, in the limit, remember our delta function is defined as the limit as delta approaches 0, we end up with this spike here. It's infinitely thin, or I should say infinitesimally thin, and it's infinitely tall, so it reaches up to infinity. However, it has an exact, precise area of 1. So if we integrate the delta function over all time, we get 1. Okay, and that's based on taking the limit here as delta goes to 0. Likewise, a shifted version of this delta function, delta of t minus tau, has just been shifted over or delayed by tau seconds, and it still has the same general features. It's this skinny, very tall spike that reaches up to infinity, but it always has an area of 1. So if we integrate the shifted delta function, it also has an area of 1. And also, one other property here, the delta function of t minus tau is the same as the delta function of tau minus t. So sometimes we deal with so-called weighted delta functions, and it's customary to attach the weight or the strength, or basically the area, integrated area of the delta function, to the arrow on the graph. So for example, if we were asked to sketch or make a plot of delta of t plus 5 delta of t minus 2 minus 4 delta t minus 3, let's see how that would look. Well, this is a delta function right here, delta of t. So I'm going to put that right here, and I'm going to just put a 1 up here to remind us that that's the coefficient out in front here. This has a weight or an area of 1. Now we need 5 times a delta function at t minus 2. So t minus 2, remember that's a delay or a time shift over to 2 seconds here. So I'm going to draw an arrow for our delta function, but remember this one is multiplied by 5, so it has a weight or an area of 5 now. And then finally, we have minus 4 times the delta function of t minus 3. So this is delayed over to 3 seconds, but because it's minus 4, there's a couple ways you can do this. I'm going to draw it pointing down with a weight of 4, or I could draw it pointing up and make sure I designate that it's a negative 4 for the area. So here's an activity for you to go ahead and make a sketch of the following function. F of t is equal to delta of t minus 2 plus 3 times delta of t minus 2 delta t plus 1. So again, please pause the video and go ahead and sketch this. So here are the solutions to the activity. The first term here, delta of t minus 2, well, that's been shifted over to the right by 2, so it's shown right here. The next term here is 3 times delta of t. So this is a regular delta function at time equals 0, but it has a coefficient or a weight of 3. So I'm going to put that above. And then the last term here is shifted to the left by 1. So it's going to show up over here when t is equal to negative 1. And it has a weight of minus 2. So depending on how you want to draw this, you can draw it pointing down. With a weight, I should probably not include the minus sign there. You can draw it pointing down with a weight of 2, or you can show it going up with a weight of negative 2. Either one here is fine. It's pretty, I think, clear what you're trying to designate. Just like in discrete time, the continuous time has a unit step function as well, and it is also called u. So in discrete time, remember, it was u of n. Here it's u of t, and the step function is it's defined as a step right at t equals 0. And notice if we shift it, like u of t minus tau, that just shifts over here to the value, whatever tau is, the step shifts over here. So here are a couple of activities, examples for you guys to sketch. The first one is sketch the function x of t, which is equal to e to the minus t times u of t. The next one, y of t, is equal to u of t minus 1 minus u of t minus 2. So again, go ahead and please pause the video and see if you can do these sketches. All right, so here are our solutions. So for the first one here, we have a decaying exponential function, which basically goes like this, but then we're multiplying it by the step function. So what that does is it zeroes out everything for negative time, and our function is going to start at t equals 0, and it will have a value of 1 because e to the 0 here is 1, and then it's going to decay exponentially accordingly, only going to the right. There's nothing to the left. It's all 0. For the second one, y of t equals u of t minus 1 minus u of t minus 2, the best way to do these types of problems, again, and we've done a few of these now, is just to sketch these two terms, maybe one on above the other like this, and then subtract one from the other. So the step function of t minus 1, well, that's just a step function that's delayed by 1. So the step is at 1 instead of 0. So that's shown right here. The second term is u of t minus 2. Well, that's just the same thing, but it's shifted over to 2. So now we need to take this function here and subtract this function down here. So the way to do this, if it's not real clear, is start over here on the left side, and notice we have 0 minus 0, which is 0, shown here. So, we keep getting 0 minus 0 all the way until we get to 1. Now here we jump up. We have 1 minus 0 is 1. So notice now our answer jumps up to 1. And when we get to 2, all right, this one is a 1. And then this one down here is also a 1. So we have 1 minus 1. So that's going to jump back down to 0. And from there, from everything, over in this region here, we have 1 up here minus 1 here is a 0 here. So our result, our answer for y of t, is a pulse like this with a width of 1 second. In continuous time, there's also a sampling or sifting property, which is very analogous to what we did for discrete time. And again, this is we're sort of jumping ahead a little bit here. This is shown in more detail in chapter 2, but since we're dealing with these the impulse delta function right now, this is a good time to show how we can use it to sample a function. So suppose we're given the following integral. We have the integral of x of t times delta of t minus tau. So x of t is just going to be some smooth continuous function like this blue line. Delta of t minus tau, remember that's a delta function, but it's shifted over to tau seconds over here. So when we multiply these two functions together, all right, remember the integrand inside here is the product of x and the delta function. So all of these values of x over here are going to be multiplied by nothing, by 0. So, and the same goes over here. All of these values of x of t are going to be multiplied by 0 down here. So the only value that comes back with any non-zero value is when it's right here at tau seconds, because that's where the delta function is. So what happens here is the delta function sitting at tau seconds forces x of t to return the value x at tau, which would be this value right here, the little black dot shown right there. All right, so this integral then, this delta function forces t to be equal to tau. So this t here we can replace with tau. Now, x of tau is a number. It's a value. It's not a function that can be integrated. So a number, of course, is like a constant. We can pull it outside of the integral. So, here it is inside of the integral, but it's just a number. So let's bring it outside of the integral, because notice this is not a function of t, which we're integrating over. We're integrating over time, t, not tau. So what we're left with then is inside this green box is we have the integral of the delta function, but remember the integral of any delta function is equal to 1 because that's the area under the curve of the delta function. So all of this goes away and all we're left with is x of tau. So basically what's happened here is this delta function has sampled the value of x of t at tau. So this is all summarized in the continuous time sampling or sifting property. The function x of t, which is again shown right here, is sampled at time tau by doing this integral here. We have x of t multiplied by delta of t minus tau, which is this delta function down here. And when you multiply these two, this function with this function together, the only thing that comes back non-zero is right here, this value of x of tau. So this x of tau is the result of doing this sampling here. There's an alternate version, which also we will encounter in Chapter 2 when we do a little more advanced topic with some of this sampling and sifting. But we can sort of swap the roles of t and tau, and we end up with this alternate version where we're basically sampling the function x of tau. Notice now this tau is our sort of like our time axis here, our time variable, and we're sampling x of tau, which is the blue line. We're sampling it at when tau is equal to t, because that's where the delta function is shifted over to. So in this case, it returns the value of x at t, which is again shown by this black dot right here. So here's an activity for you to test your skill here at this continuous time sampling. So suppose we have a function x of t is equal to t to the 4th power. You're asked to evaluate this integral here. It's the integral over all time of x of t multiplied by delta of t minus 2. So in order to do this, remember, you can go back to the previous slide and look at the sampling property. Okay, so the solution to that activity was we're going to write, here's our integral, the integral of x of t times delta of t minus 2. Now this delta function here is basically selecting or forcing t to be equal to 2. And so we can change this t right here, x of t becomes x of 2. And x of 2 is just the value of this function when t is equal to 2. So we can pull the x of 2 out in front of the integral. It's no longer a function, it's just a number. And then of course this integral, what's left here, has a value of 1 because it's the integral or the area under the curve of this delta function, which is always 1. So our answer is x evaluated at 2, so we have 2 to the 4th power, which is 16. And that is the end of this part of the video. We will return for part 4, the last part of Chapter 1 next. Goodbye.